everyone, this is Swathi, working as Assistant Professor in the Department of Electronics and Communication Engineering in Institute of Aeronautical Engineering, Dundigal. Welcome to this lecture. In this lecture, we'll discuss some tutorial questions or its question bank on Module 4, that is Minimization of Boolean function and Combinational Logic Circuits. So we have seen how to simplify a Boolean function using K-maps and tabular method in this module, and also how to design a combinational logic circuit. So we have various types of logic circuits, combinational logic circuits like adders, subtractors, multiplexers, demultiplexers, encoders, decoders. So we will be discussing how the questions are asked on this module. Okay, so simplify the Boolean function f of a w comma x comma y comma z summation m is m of 1 3 7 11 15 plus summation d of 0 to 5. So as you can identify that it is a 4 variable function, just draw the 4 variable k map and group all the adjacent cells and write down the prime implicants for that. So then you will be able to get the simplified Boolean function using K-maps. So while grouping, you have to keep one point in mind, that is always you have to try to group maximum number of adjacent cells first. That means you need to form higher groups. Then you have to, if not possible, then go for the next higher group. So that is how you can solve this problem. And here, these are the terms which indicates that m of summation m of, it is given in SOP form. So that means you have to draw the K-map like this. Okay, so W, X, Y, Z, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, right? So for all these minterms, the function output is considered to be 1. So that is 1, 3. Next, it is 7. Okay. Next 11, 8, 9, 10, 11. Next 15. So this is the function. And don't cares. These are the don't care terms for which the function output is considered to be don't care. That means it is not specified. For 0, 2 it is don't care, and even for 5 it is don't care. So this kind of mapping should be done. Okay, and then grouping. How can we group? So I can group these 4 and I can group these 4. So that 4 quads are covered. I can write down the prime implicant for this so that I can get the simplified Boolean expression. And simplify the Boolean function f is equals to summation m of 0, 1, 2, 3, 4, 7, 9, 10, 14, 15 using tabular method. So I have a video on tabular method. So you just go through that video. In that I have given you the procedure for simplifying the Boolean function using tabular method. So the same fashion you can solve this question. And what is a decoder? How do you convert a decoder into a demultiplexer? How to answer these questions? First, define a decoder. Decoder is a combinational logic circuit which can be used to convert a given binary data into decimal data, and whose size is given by n by 2 power n. N by 2 power n. So that means here we do have a block diagram for this one. We have n inputs and 2 power n outputs. These are the 2 power n outputs. These are the n inputs. This is n by 2 power n decoder, right? So this is also having an enable input. So like that you have to mention what is a decoder. And then how to convert a decoder into demultiplexer. Only the thing is, now here also you have to define demultiplexer. And what is the size of a demultiplexer? So the size of a demultiplexer is 1 by 2 power n. So the outputs are same in case of demux and decoder. Only the thing is input is 1, whereas in decoder we have 2 inputs. Whereas not only this, we can also have n selection inputs in demultiplexer. So the thing is, first write down some basic things about decoder and basic things about demultiplexer. Now how to convert a decoder into demultiplexer? So what do we do? What should we do is connect the enable input to the data input and consider the n inputs of decoder as n selection lines of demultiplexer and 2 power n output lines as the output lines of demultiplexer, so that I can implement a demultiplexer using a decoder. Only the thing is, consider the enable input as data input, and all the inputs of decoder are considered as selection inputs. That's it. Simplify the following function using K-map and implement them using logic gates. So here the function is given. So now I want to implement it using K-map. So functions are given. So in order to simplify this, first we need to convert this into canonical form. So we need to check whether each term is having all the variables or not. If not, we need to make all the variables are present in all the terms of the given function, and then map that given function with the K-map and form the groups with the adjacent cells and simplify the Boolean expression. So it is not in canonical form. So first convert it into canonical form, then map with the K-map. How many variable K-map is required here? 4 variable K-map. Take a 4 variable K-map, map them. So it is already in the canonical form, so no need to do that. So simply map this Boolean function with the K-map. Okay. So that is how you can simplify. Now realize the Boolean functions using half subtractor, expressions for half subtractor. So define a half subtractor. Just draw the block diagram of half subtractor like this and give the truth table. So where the truth table consists of 2 inputs and 2 outputs. Just write down some few concepts about how the difference output, when the different output becomes 1 and when the borrow output becomes 1. Just write down few sentences about this. And then get the Boolean functions for this difference and borrow output using K-map like this, and implement this using logic gates. So this is a logic circuit for this half subtractor, which can perform the subtraction of 2 bits, okay, and produces 2 outputs, difference and borrow. So next, implement full adder using half adder and 1 OR gate. So how can we implement a full adder using 2 half adders? So justify them using Boolean expressions. Okay, first how can we implement a full adder using 2 half adders? Just justify using Boolean expressions. Okay, that we have discussed in the theory class. Just go through that video lecture so that you can understand how can we justify that we can implement a full adder using half adder. So draw the block diagram. So for implementing full adder using 2 half adder, we require 2 half adders and 1 OR gate. So this is our block diagram and this is the logic circuit. Okay, so this is how you can implement a full adder using 2 half adders and 1 OR gate. And construct a full adder using Boolean expressions. So same thing, define a full adder, draw the block diagram. So how many inputs we have? 3 inputs, A, B, C in, and 2 outputs, sum and carry, and draw the truth table. So a truth table consists of 3 inputs and all the 8 possible combinations of 3 inputs and the possible output, sum and carry for that 8 combinations. And then derive the Boolean functions for this sum and carry using the K-map. Okay, so first get the expression for sum and carry using K-map, and then draw the logic circuit for that. So this is the logic circuit, truth table and block diagram of this full adder. Now design an 8x1 multiplexer using 4x1 mux. So before answering this, first you define a 8x1 multiplexer, define a 4x1 multiplexer, draw its truth table. Okay, then you just implement that 8x1 multiplexer using 4x1 mux. So 8x1 mux is having 8 inputs. Okay, 3 selection inputs and 1 output. Whereas 4x1 mux is having 4 inputs, data inputs, 2 selection inputs and 1 output. So how to implement that? So as we need to have 8 inputs, so we need to take 2 4x1 mux. 2 4x1 mux we are taking, and 2 selection inputs that are least significant selection inputs are given as the selection inputs to the 4x1 mux in as common, and I0, I1, I2, I3 are given as input to the least that is lower 4x1 mux, and these are given to the upper 4x1 mux, I4 to I7. And then we have 2 outputs available. So among them, I need to consider only I need to select only one. So again I'm using a 2 by 1 max. So this is how. So whereas the MSB is given as the selection input to the next level of multiplexer. So that means S2 is given as selection input to this. So based on this S2, any one of this two input lines will be selected and that will be sent to the output. So this is how you can draw the or else implement a 8 by 1 max using 4 by 1 max. Construct a 3 to 8 decoder using AND gates. So we need to construct a 3 to 8 decoder. First define a decoder and what is a 3 to 8 decoder. So draw the block diagram, give its truth table and then get the Boolean functions of all the outputs and implement them using logic gates. So this is the how you can implement, you can answer this question. Now part B, construct logic circuit to convert gray code to binary code. So gray code to binary code. So this is a combination logic circuit design. So first write down the procedure for designing a combination logic circuit. So what is that? First identify the number of inputs and identify the number of outputs. Develop the truth table and get the Boolean expression for all the output variables in terms of input variables and then implement them using logic gates. These are the steps, right? So this is the truth table. Write down the truth table of conversion of binary to gray or gray to binary and then get the Boolean function for what we are doing. We are doing gray code to binary conversion. So that means these are considered to be inputs and these are considered as outputs. These are considered as outputs. Now I want to get all the outputs that is a B3, B2, B3, B2, B1 in terms of G3, G2, G1, G0, right? So like that you get the Boolean functions. These are the Boolean functions. So from which I am getting the Boolean functions for this. Then draw the logic circuit for all these Boolean functions. Okay, so this is how you can design a binary to gray or else gray to binary conversion. So this is also the same thing. So in this case, binary code to gray code. Binary code to gray code means binary is the input and gray code is the output. So now I have to get G3 in terms of B3, B2, B1, B0 and G2, G1, G0 also in terms of B3. So that means we need to draw the K-maps for all these four. Once we got the Boolean functions, minimized Boolean functions, just implement them. Realize the Boolean expression for FullSubtractor and draw the logic circuit. FullSubtractor, which can perform the subtraction of 3 bits. So A, B, borrow in and the outputs difference and borrow output. And this is the truth table for FullSubtractor, which is having 3 inputs, 8 possible combinations and 2 outputs. Draw this truth table and get the Boolean functions using K-maps here and then draw the logic circuit. So this is how you can implement or you can answer this question. And explain a 4-bit carry look ahead adder with neat circuit diagram and relevant expressions. So this is the truth table for carry look ahead adder. Okay, and these are the relevant expressions and this is the logic circuit for that. We do have carry, generate and propagate function. This is a logic circuit for implementing the carry, generate and propagate functions. And by using this, we can implement a 4-bit carry look ahead adder. This is a 4-bit carry look ahead adder. By cascading all the carry, generate and propagate functions, we can implement a 4-bit carry look ahead adder. Okay. Now implement 64 by 1 mux using 8 by 1 mux. For implementing 64 by 1. So how many 8 by 1 mux we require? We require 4 8 by 1 mux. So this is 8 by 1, 8 by 1, 8 by 1, 8 by 1. So how many inputs we have? 8 inputs we have. Every mux is having 8 inputs. So like that, how many inputs we have? 8 into 4. That is, 8, 8, 16, only 32, right? So like that, we need to have 8 mux, 8 by 1 mux, so that I could get 64 inputs. So 8 inputs we should take, 8 mux we need to take, and then all the 8 inputs or 8 outputs of these mux are given again back to the 8 by 1 mux. So 64 by 1 mux means 6 selection inputs we have. 6 selection inputs. So the least significant, that is, we have to give S0, S1, S2 as the selection input for the first section, whereas this is also having how many? 8 inputs we have. 8 inputs we have. Again, this requires 3 more selection lines. So that is S3, S4, S5. And finally, we have one output. So like that you can implement. Okay, so this is how you can, that means all the first 3 selection inputs are, that is S0, S1, S2 are applied as common selection inputs for this, and then among them the remaining selection inputs are given as the selection inputs for the next 8 by 1 marks, so that I can get, or else I can implement the 64 by 1 marks using 8 by 1 marks. Explain the working of 2 by 4 decoder. Also implement a 2 to 4 decoder using 1 to 2 decoder. So this is a 2 to 4 decoder block diagram and its truth table. Now we want to implement a 2 to 4 decoder using 1 to 2 decoder. So this is 1 to 2 decoder. Okay, this is also 1 to 2 decoder, right? 1 to 2 decoder is having two outputs. So let us consider this as Y3, Y2, this as Y1, Y0, and we have one input. Okay, so here these inputs are nothing but this is A1 and this is A0, whereas the enable input, okay, so these are, let us consider this A0 is given as common to both, okay, whereas this is given as A1 and this is complemented and given back. So this is nothing but our enable input, So this is the implementation of a 2 to 4 decoder using 1 to 2 decoder. You can, if you want a clear cut explanation, you can just go through the theory class which is uploaded in the YouTube. Now implement a full subtractor using half subtractor and justify with Boolean expression. So how can we implement a full subtractor using half subtractor? You justify with the Boolean function. You just take the Boolean expressions of full subtractor and you can implement that. You can justify them. We can such that we can implement it using two half subtractor. Okay, and this is the block diagram. Draw this, and then this is the implementation of full subtractor using two half subtractor and one OR gate. A half subtractor is having one XOR, one AND, and one inverter. So this is the implementation of full subtractor using two half subtractor. And finally, we have some more questions. Simplify the following Boolean function using tabular method. So using tabular method, so just go through the algorithm of tabular method, how to simplify the Boolean function using tabular method. So while we have don't care conditions included in the Boolean function, while constructing the table, you need to consider these don't cares also. While grouping the main terms, you should consider the don't cares. But while constructing a prime implicant chart, we should not consider the don't cares, because don't cares are not needed to be covered in by any group. So that is why no need to cover this while forming a prime implicant chart. So that point you have to keep it in mind and go according to the algorithm of Queen-McCluskey and try to simplify this function. And construct a 16 by 1 max using only 2 by 1 max. Only 2 by 1 max. So how many 2 by 1 max we require in order to implement 16 by 1 max? So 8 2 by 1 max we require. So 8 outputs we'll have. And again we need to have 2 by 1 max in the second section. So again, as 2 by 1 max we have in the 8 outputs we have. So again in the next section we should have 4 more 2 by 1 max, and in the third level 2 more, and then in the last level we should have 1. So like that 4 levels of 2 by 1 max we need to use. And how to assign this LSB, that is selection lines. LSB to the first section and MSB to the last section. So like that you can assign the selection lines for each and every level, and then you can implement it using 16 by 1 marks. 16 by 1 marks using 2 by 1 marks. Sketch the full adder using logic gates. Just define a full adder, draw its truth table, give its Boolean functions, and implement them using logic gate. Draw the full adder using NAND gates. Sorry, half subtractor using NAND gates means first you have to draw the full half subtractor. How to draw the half subtractor? Give its truth table, get its Boolean functions, and then implement using logic gates. And go through the procedure of implementation using NAND logic. Just implement that full subtractor using NAND logic. And then full subtractor, the same procedure. And draw a full subtractor using NOR logic. So we know the implementation of any Boolean function using NAND and NOR. You just apply that procedure and simplify this. And draw a full adder circuit using NAND gates. These are all of same kind. You can just go through that procedure and you can implement it. Explain the differences between multiplexer and demultiplexer. While answering this question, first define a multiplexer, give its block diagram. Define a demultiplexer, give its block diagram. And list some of the differences between the architectural and functional differences between the multiplexer and demultiplexer. Define prime implicant, and essential prime implicant. Just define them. If it is asked for long answer question, just give the definitions of implicant, prime implicant, essential prime implicant, and take one example of Boolean function, map it with the K-map, and then identify the prime implicants and essential prime implicants from that K-map, so that you will be getting, the answer will be very clear and you will be able to get full marks in that. So we explain with examples so that you will get good marks here. So these are all the questions, long answer questions that may be asked on the that may be asked on the Boolean expression. So that's all for this lecture. So in this lecture we have seen what are the different kinds of questions that may be asked on module 4, that is on the minimization of Boolean function using K-map and tabular method, and also we have seen some of the implementation of combinational logic circuits using logic gates. So that's all for this lecture. I hope it is clear to you all. Thank you everyone.
Like, share and subscribe. Hit the bell icon for more updates.